Hello students, today we will discuss about transistors. So transistors are consisting of two PN junctions which are formed back to back. So if you check the construction, it would be formed out of a single piece of semiconductor. So here is a representation, and where you can see a region, P region is sandwiched between N and 2N type material. That means we have dot on one side, on either side with N, and the middle portion is remain undot or P dot itself. Okay, so that is a way of sandwiching one type of material between the other type of material. So that will constitute two PN junctions back to back. Here you can see an NP and PN junctions are there. Similarly, another possible way of representing is you could actually have N type material sandwiched between two P type material. So here also two PN regions, PN again NP, two back to back PN junctions are obtained. So such a terminal, such a device is called transistors, and transistors have three terminals: emitter, base and collector. And what is the speciality of emitter? Emitter, as the name suggests, it supplies the majority carriers. So in order to do so, it must be heavily doped. While the base is a very thin one, it is very lightly doped, and collector, as the name suggests, it will be collecting all the majority carriers coming from the emitter. So that is applicable for here also. So can represent in a circuit, a symbol for representing transistor is so and so. So here you can see a middle portion is given by a base line, and two lines are diverging outward, which represent emitter and collector. And in order to distinguish it from whether it is an emitter or collector, what we do is that we will mark an arrow mark. An arrow mark denotes the current flow, the flow of positive charge from P region to N region. Okay, that is how. Hope you remember how we have represented the diode. That was also represented indicating the current flow. So always from P to N, the flow indicator we have used an arrow mark shape like this. So here also in an NPN transistor, P is at the base. Okay, so the arrow mark will start from P, so the arrow mark will moving outward. While in the case of PNP transistor, the arrow mark must start from P and go to base. So it is like this. So this is how we differentiate whether it is an NPN transistor or PNP transistor. PNP transistor can be denoted by looking at the inward or outward direction of the arrow mark represented in the emitter. So if this is outward, which means the base is P and the remaining portion will be N and N terminals. So it is a NPN transistor. How do you identify this transistor? The arrow mark is like this, which means this region is P and it is going to N region. So now you can complete the other region, which is P. So it is a PNP transistor. So one thing is that we can identify which transistor is it based on the direction of the arrow mark, and second thing is that we can distinguish whether it is an emitter terminal or a collector terminal, because arrow mark is present only on the emitter terminal, because that is the supplying majority carrier. So now let's see how a transistor works. Transistor's normal operation requires the emitter base junction to be forward biased and the collector base junction to be reverse biased. So forward biasing will facilitate the flow of majority carrier. So here you can see the P region consists of the majority carriers as holes. So what happens, the P region as a P type is connected to the positive terminal to make it forward biased. So this positive charge will repel or push the holes towards the base region, and base consists of very few number of majority carrier, that is electrons, compared to the P region here, because it is a very thin region and it is very lightly doped. So the majority carriers electrons present in N region is very less compared to the incoming holes. So few of them, very few, maybe like 2% of them will 2% of the holes coming from the emitter will be recombining with the electrons in the N region, and the remaining 98% will be reaching on to the collector. So collector is reverse bias, which means P region is connected to the negative terminal, opposite polarity. So since they are giving an opposite polarity, the negative terminal will try to attract the holes. Holes are positive, so it will try to attract the holes coming through the base. That is how the working happens in a transistor. And another feature, you can see that the collector here is more, collector is given a more voltage than the input voltage, because the collector has to attract all the majority carrier. So it is given a high potential than the input circuit. So you can consider this as an output and this as an input circuit. Okay. And so how do you represent charges? So how do you represent the voltages? So here you can see that it is a voltage applied between collector and base. So we can give the applied voltage as VCC, and what you obtain as a potential difference as, we can represent it as either as VBC or VCB. But we will be representing it in only one way in a particular case. So in PNP transistor, we can see that this collector is more negative than the base. Base as well as collector are connected to the negative terminal, and you can see that collector is more negative than base. So which is positive then? Which is less negative? That is base. So it will be represented with the less negative thing as first number, first subscript, and followed by the C. So we represent the potential difference across B and C in an PNP transistor as VBC. While in the case of NPN transistor, the potential difference will be represented as VCB, because here collector is, both collector and base are connected to the positive. So we represent the first digit as with more positive. Which is having more positive? Yeah, collector is having more positivity. So C denote collector followed by B. So that is how a voltage drop potential difference is mentioned. And another feature, you can see that the current from the input supply is, it is not shown. Okay, so we are getting a current from here, which is IE, emitter current. So emitter current is flowing through this, and it is divided into two over here. One is IB and other is IC. So you can consider for all circuits, the emitter current will be sum of base current and collector current. So whatever holes coming from the emitter is splitted up as base current, maybe some 2% and some 98% as collector current. Similarly here also. Okay. So now let us come to the common emitter configuration. That means we can connect the transistors in various configuration. As you are aware that there are two circuits, that is three terminals. So one is input and other is called output circuit. Okay. So we can connect, one terminal will be common to input as well as output. So based on that, you could have common base, which means base will be common to the input and output circuit. This is such a circuit. Here you can see base is applicable to input as well as output. So this is a common base configuration. We can also have common emitter configuration, which means emitter will be common to input and the collector, input and the output. So here you can see emitter is connected to the input circuit as well as the output circuit. Okay, so input supply is given between base and emitter, while output is supplied between collector and emitter, again emitter. So common terminal is emitter, and hence such a configuration is called common emitter configuration. So let us see what is the biasing given. So here you can see the input must be always forward biased and output must be reverse biased. So input nammal nokki kazhinjal the arrow mark is showing into the base. So what does that mean? Can you identify the transistor here? So this emitter must be P, base must be N, and hence collector must be P. So what kind of transistor it is? It is a PNP transistor. Okay, and input must be forward biased. So input must be always forward biased. So how do you make it forward biased? The base region, which is an N-type material, must be connected to N terminal of the, or the negative terminal of the battery, while P region, which is a emitter, must be connected to the positive terminal of the battery. Then it becomes forward biased. Similarly, in order to make the output to be reverse biased, what is to be done? Collector is a P region, so it must be connected to negative, opposite polarity, that is negative terminal of the battery, while emitter is a P region, it must be connected to the positive. It is connected to the positive. That is how it is given. Okay, so we need to bother about this collector alone. Collector is given negative. That has to be bothered. Next thing we need to consider it is current amplification factor beta. So current amplification factor is usually, for any circuit, it is considered as what is the output current to the input current. So in this case, output current is collector current and input current is base current. So in the common emitter configuration, current amplification, how much enhanced current is obtained, that is given by beta, and beta is evaluated as IC by IB, which is output by input current. Okay, and we know IE is IB plus IC. So instead of IC, I can write in from here IC is equal to beta times IB. So we make use of beta times IB. So here you can see emitter current is just IB into 1 plus beta. Okay, so that is the current flowing in the emitter. Okay. Now there are certain things to be remembered in the common emitter configuration. So suppose there is no voltage supply happening in the input. That means IB is 0. Input current is 0. So in that case, we expect, if there is no input, we expect that no output is obtained. But in spite of base being disconnected, അതായത് ഓപ്പൺ ആയിട്ടിട്ടാലും you will get a current flow. Okay, and that current is called leakage current. And what is the reason for leakage current? We know the common emitter junction is reverse biased, which means it will be reverse biased, means this is the what kind of region? It is a P region and emitter is again a P region. So the P region has holes as the majority carriers, isn't it? So holes are facing the negative terminal of the battery. So what will happen? Holes will be attracted towards this. So it is a reverse biasing for the holes alone. Holes is connected to the opposite polarity, which means reverse biasing for the majority carrier. But for P-type region, in addition to the majority carriers, it has minority carrier. What is the minority carrier in P region? Electrons. So electrons in it is connected to the negative term. So they are connected to the same polarity. So what does minority carriers feel? Minority carrier feel that they are connected to the same polarity, which means they are forward biased. And how do we get minority carrier? They are generated thermally. എത്രയാണോ ടെമ്പറേച്ചർ അതിന് കറസ്പോണ്ടിങ് ആയിട്ട് ഒരു thermal energy കിട്ടും, which is given by KBT. That will be enough to make some or break the sum of the covalent bond and make some few electrons free. And those are the minority carriers in P region. While the majority carriers are contributed by doping. Okay, so that is the difference. So in collector emitter region, though it is reverse biased, it is forward bias for with respect to minority carrier. So what would they do? If it is forward bias, they will of course flow. Flow ചെയ്യും. So minority carrier flow ചെയ്യുന്നതുകൊണ്ടുള്ള കറൻറ്റിനെയാണ് we call it as leakage current. Because it is between collector and emitter, we call it as collector emitter leakage current, ICEO. And it is seen that the total current will be consisting of IB കൊടുത്തിട്ടുണ്ടെങ്കിൽ അതും വരും plus 1 plus beta ICO. Okay. So we need to remember this. It is not due to the input IB alone. It is also due to leakage current, and leakage current is the coefficient is given by 1 plus beta times ICO. So here you can see that any slight increase in leakage current will lead to beta times. So beta is actually in the range of 500 and all. So 500 times it will be a very huge value. So a slight increase in leakage current will lead to a huge or marked increase in collector current. Okay, so what you can see is that if temperature increases, minority carriers will be more, and hence leakage current will be increasing. If leakage current increase, it is related to collector current, so collector current will increase. If collector increase, what happens? There will be power dissipation, more amount of, because it is reverse biased, right? So reverse biasing current flow കൂടിക്കഴിഞ്ഞാലും voltage drop വളരെ കൂടുതലായിരിക്കും. Power dissipation of the diode will increase. So power dissipation കൂടുവാണെങ്കിൽ എന്ത് സംഭവിക്കും? Temperature of the junction will increase. Temperature കൂടും, again what will happen? It will again increase the collector. So there is a cycle happening, cycling of increasing in temperature and current is happening. And at a particular point, the current collector current will be so huge that it will be beyond the safe operating value. Then it would damage the transistor itself. Such a condition is called thermal runaway. So whenever there is a temperature increase in temperature, it will increase the leakage current, in turn increasing the collector current, and which in turn increase the power dissipation and hence heat up the transistor, and the cycle continues. So once at a particular point, IC will be very large enough that it will damage the transistor. Okay, so let us coming back to common emitter configuration. Here you can see we are applying a voltage as VB, and the output is measure. Output circuit consists of a voltage VCC, and you can see there is a voltmeter connected here in the input circuit as well as in the output circuit. So input circuit voltmeter will measure what is the voltage potential difference between base and emitter, and hence it is given VBE. While the output voltmeter will measure what is the potential difference between collector and emitter. So it is given as VCE. Okay, and there is ammeters for measuring the current. So this is and what is this represent? This represent a rheostat, which means we'll be changing the rheostat so that we can adjust what will be the voltage drop across the resistance. So that much will be communicated or given to the base. So we'll be using a battery, and by changing the rheostat we can adjust the value of voltage, supply voltage given to the input. So similarly, you are connecting a supply in the output circuit parallel to the rheostat, and rheostat can be changed so that corresponding voltage will be changed, and so we can change the amount of voltage given across the collector and emitter. So this is the test circuit used for studying the common emitter configuration. So we will be studying the input characteristics, output characteristics, and current characteristics. So first one is input characteristics. So input characteristic means we will be keeping VC, that is output will be kept constant. VC is kept constant and hence input VI characteristics input current IB and input voltage VB. So we'll measure what is the change in current with the change in voltage. Okay, so input voltage input current variation study we call this input characteristic, provided we are keeping output voltage constant. So keeping in mind, we'll be getting a plot like this, VB versus IB. So in this curve we can see that this is if you take the change, the slope of this curve, it is delta IB, that is delta Y by delta X. Change in Y by change in X will give the slope. So here delta Y corresponds to the change in current and the delta X corresponds to the change in voltage. Okay, so the slope is given by change in current by change in voltage. But what you require is resistance. So what is resistance? Resistance is given by voltage, change in voltage divided by change in current. So we can see that in order to measure input resistance from the input characteristics, you just have to plot this VB versus IB and taking the inverse of slope. Slope is IB by VB. So inverse of slope will give the input resistance. Okay, and the range of input resistance would be of the range of kilo ohms, 1000 ohms. But in this particular region, this would be of the range of 600 ohms and all, because the current has increased. Resistance. Okay. Next is output characteristics. So similar to what we have done in the case of input characteristics, we will study the variation of voltage and current, VI characteristics. So what is output here? VC is the output, and what is the current? IC is the current. So the variation of IC with respect to VC will be studied, but here instead of keeping the input voltage constant, here we will be keeping input current a constant. That is the difference. So keeping input current constant, that is IB constant, we will study the variation of voltage versus in output current, output voltage versus output current, that is VC versus IC. And what you can see is a plot like this, and so this represents, so the first curve represents the variation of VC versus IC for a particular IB. And here you can see IB value 0. 0 current aanengilum, input current is 0 aanengilum, you will be getting a current, and we have mentioned it, that is called leakage current, which is due to the thermally generated minority carrier. And if you increase the input current, you can still find out the variation between output voltage and current, output current. So the pattern would be like this. So more current will be seen for the change in voltage. And if you still increase the input current IB to 40 microampere, then also you can see the IC or the output current has increased. Similarly, we can do it for different ranges of the input current and study the variation. And there are certain features to be studied from this plot. The first thing is that if you measure the slope also here, Y versus X, so that is delta IC versus delta IC to delta VC. So from which we can write down what is output resistance. Any resistance is written as voltage by current. So in this case, output resistance means output voltage, that is delta VC, change in output voltage divided by change in output current, that is IC. And looking at the slope, here you can see that output current is just the inverse of slope. And it would be ranging in the range of 50 kilo ohms approximately. And we can also find out current amplification factor directly from the output characteristics itself. That is, we need to just consider any two changes, curves for the IB. For example, if you consider current 60 microampere and 40 microampere for base currents, and if you consider these 2 points, this corresponds to IC value. So IC values are different. So for the same voltage, IC value are different. Okay, for different base currents. So that change can be noticed delta IC. So we know what is the change in IB base current and the change in output current. So from which we can calculate the current amplification factor beta delta IC by delta IB. Okay, and the other thing we need to look at is that there is a region called saturation region. So what does that saturation region implies? So we can see that as we start giving the voltage, there is a sudden rise in current and then it comes to the saturated value. So this saturation will depends upon what is the input current being given. Okay, so this region is called saturation region, which happens for very low values of in output voltage VCE. And here we can see that the change in base current will not produce a corresponding change in current. Okay, so here you can see that whatever be the value of IB, the change in IB will not produce a change in current. Okay, so and hence it is called, or this particular region you can see. Okay, this is called a saturation region. Then the region is cutoff region. So in cutoff region, it is that region where the main current is 0. Okay, main current, collector current, that is, if you give IB as 0, input supply kodutillengile IB will be 0. So in spite of input being open, you are getting a current flow across the collector emitter, which is due to the leakage current. So that in that region there is no main current, it is only due to the leakage current. So that region corresponds to a cutoff region in the case of a normal operation of a transistor. And the third region to be considered is the breakdown region, that corresponds to a huge value of VCE, which means beyond that particular voltage you will get a sudden increase in current, so which will leads to the damaging of the transistor as such. So we won't be working in the breakdown region. Okay, and the third characteristics we have to study from common emitter configuration is the current transfer characteristics, where we will consider the change in output current with respect to input current, that is IC versus IB, provided we are keeping output voltage a constant. So from which you can calculate the current amplification factor as explained before, delta IC by delta VB at a constant output voltage VC. Okay, so that would be of the range of 500. Okay, and you can see that for a given IB, when IB is 0, you are still getting a current, this much current, and that current will is due to the leakage current, denoted as ICE. Okay, so that ends our topic. So thank you.